So we need to keep in mind that the encoding of the free functor uses here z as the existential quantified type. To get a little more intuition about how the existential quantified type works, let us consider a simple example similar to this one, where you have existential quantified type z with a function mapping it to something and another piece of data containing that type. So consider this type expression. Just temporarily, I denoted this by PA. And we will now show that PA is actually equivalent to the type A. The Scala implementation of PA would look like this. We would have a sealed trait and a single case class that hides the type Z. Now imagine we would like to construct a value of PA where A would be some fixed type, say integer. In order to construct it, we would have to use the case class PZ, and we would have to give some value of a type Z and a function from Z to A. So imagine that we have the type Z equal to A. Well, it's our choice. We can choose that. We give a value of type A, and here instead of this function we give identity. We can always do that for any type A. And so this means we can always build a value of this type if we have a value of type A. So that gives us a function that converts from a value of type A to a value of this type. Just inserting identity function here and inserting the value A here and setting Z equal to A. So we are free to choose what Z is when we construct the value of this type. So this gives us the equivalence function in one direction from A to P. Now, how about extracting A from P? If we have a value of this type, we actually cannot extract Z out of it. So the value of this type contains a Z as part of it, but we don't know what the type of Z is. And because the type Z is hidden, we cannot extract it out of the function PA. We cannot have a function whose type is unknown, whose type signature contains an unknown type. However, what we can do is we can extract A out of PA. In order to do that, we need to apply this function to this value. This is the code. And we don't need to know what the type Z is. This would be some unknown type, but the function f has the right type signature so that we can apply it to that value. So this is a well-defined value. And so in this way, we can extract a value of A out of PA. Now, actually we cannot transform PA into anything else other than into a value of type A, because this data only allows us to get a Z or to get this function or to apply this function to this. Now, we cannot get a Z out because we don't know the type of Z. We cannot get this out because we don't know the type of this function. So we cannot write code that says take a P and output some unknown type. That doesn't work in Scala. that the result type of a function must be given, must be fixed before you can write the code of the function. So this means this value is observable only via this function. So the only way of doing any computations with this PA is to apply this extracting function and to get an A out of it. And so if you wanted, for example, to compare two different values of type PA, then you cannot directly do that because you don't know what Z is. You cannot look into it, it's hidden. So the only thing you are then forced to do is to extract an A out of this and compare the resulting values of type A. And so for this reason, the functions A to P and P to A are inverse to each other when we use P to A in order to compare any values of type PA. So this can be shown relatively easily if you, for example, take a composition of A to P and P to A in one or another direction, and you can substitute the code. In one direction, this would be identity of Z, so that's clearly going to be identity. In the other direction, you have this, and this should be equal to the result, so this A equal to P to A of some P, and that should be equal to that P in order to show the isomorphism in the opposite direction. So that requires us to compare two different values of type P of A, and we have to do that by applying P to A to both sides, and that's what will again give us identity. So I skip this calculation, but this is very similar to what we did for proving the identity of types a couple of slides before, when we used the universally quantified type. So this proves this equivalence. And actually there's a stronger version of this equivalence, which is this. If you have a functor f, so this is not a free construction, this is just a given functor, then this is equivalent to that functor. And this is proved in a very similar way. The only way to observe a value of QA, in other words, to compute anything out of it, is to extract an FA out of it. You can extract an FA by taking FZ and doing fmap with this function. And you can't extract anything else. You cannot extract an FZ out of it because you don't know Z. You can't extract this function out of it because you don't know what this function is, what the type of this function is. So the only thing you can get out of this QA is some value of type FA. So that's the transform Q to F. F to Q is similar to this one. You take an FA, you take identity function, and very similarly we can show that these two are observational inverses. Now they are not directly inverses in a sense because you cannot directly compare values of this type because it contains some unknown type Z inside, and what if this type is different? However, this type Z is not observable even if it's different. So you have some value of QA with one Z and another value of QA with another Z, you cannot see that the type Z are different in these two values. You have to first extract the observable value out of this, which is a value of this type. Once you have extracted it, you compare those. So this is what I mean by observational equality. And so you can show that these two functions are inverse of each other when the equality is understood as observational equality. So whenever you compare values of this type, instead you extract FA by using this function and compare the resulting values. So this is how the existential type works. Now in the free functor construction, we use the existential type and we can rewrite the construction using this type expression. So I've just taken this code and I have rewritten it using the type notation that I'm using. So that is the definition of the free functor. So this is a recursive definition because we're reusing the type ff itself as we are doing here. So ff is reused as part of one of the case classes. So this is the tree encoding. In other words, this encodes the unevaluated expression tree of an expression obtained from the free functor values and operations. So there are operations which are insert an FA into the free functor and apply a map to a free functor. So using these operations in any order, we get arbitrary values of the free functor. So let us derive a reduced encoding. To derive the reduced encoding, we start from the tree encoding. We try to see how we could simplify values of the tree encoded type using the laws of the type class. So the functor type class has two laws, the identity and the composition law. And composition is also associative, so that's another property. So we need to see if we can simplify values of this type. So let's consider values of this type. Any value of this type must be, by construction, either a wrapping of this, or it will be a previously constructed value of this type multiplied by a function like this. So essentially we have to start with some wrapping and then we multiply a few times. Every time we multiply, so we use a map function. Every time we do that, we add another existential type parameter. So then we have all these existential type parameters. Then we have the first wrapped value of this type constructor f, which is not necessarily itself a functor. And we have a bunch of functions of different types. Now, all these functions must be composed associatively. In other words, the law of composition is that the result of mapping with this function and then later mapping with another function and then later again mapping with another function must be the same as a result of a single mapping with the composition of all these functions, and the composition is associative. So in other words, we should be able to simplify this value into a product of this and this single function here, which is composed out of all of these. And the result of the composition doesn't depend on the order in which we evaluate the composition because of associativity. So therefore, by using these laws, we can simplify this expression into this expression, where there is only one quantified type. All of these other types are not visible anymore because we're not using them. And there's only one function here. Or also, there's a possibility that we just have this and no functions. And this possibility should be equivalent to having this value mapped with an identity function because of the identity law for functor. So therefore, we can say, let's just always have this type. And if necessary, we put identity function here. And we always have some value of type constructor f. And we always have a single function, but we no longer have disjunction because we can represent this case by putting an identity function in here due to the identity law of the functor. So this concludes the derivation of the reduced encoding. So the result is this formula, which means we have successfully simplified this expression. We got rid of the disjunction and we got rid of the recursion. This is non-recursive. We don't use the recursive instance anymore. We just found that it's equivalent to have just a type constructor f. And that's the reduced encoding of the free functor. So the only important remark here is that it requires a proof that actually this is a reduced encoding. So by definition, a reduced encoding is such that it respects the laws. So if you apply, for example, map to a value of this type with identity, the result must be equal to this. So it is not true for the tree encoding. The result will have an extra function here, an extra existential type, and so on. And that's kind of not good enough for reduced encoding. It must not be there. So reduced encoding must satisfy the laws. And that's what it does. So it requires, nevertheless, some ingenuity. We have to derive it. It doesn't follow automatically what it should be. And the proof that it is equivalent to the tree encoding and satisfies the laws. Another good result from reduced encoding is that we can see what happens when the type constructor from which we generate the free functor is already itself a functor. So if we are taking a free functor of a type, over a type constructor that is already a functor, then, as I already said, this expression, which is that, is equivalent to the functor itself. So this type is going to be equivalent, which means that, well, there's no harm done encoding this free functor, except maybe performance will suffer. You have some extra stuff, we'll have some identity function here, or some other function. Basically, you are just postponing the map. There might be some advantages in doing that, which I will show, because you can make this stack safe. But this will certainly be a performance hit. So don't do this if the type constructor is already a functor, if you can avoid it. But there's no harm done. It's the same equivalent type, so you won't have more information somehow. So this is an interesting property, because usually what happens with free constructions is that they wrap your generating type in some stuff, and so they add information to it. And so the resulting type is usually not equivalent to the type constructor that you're wrapping. But in this case, it is equivalent. So for functors, functors are special. And free functor over a functor is equivalent to that functor. So that's a special property. Finally, let's look at the church encoding. Now, this is a more challenging task because we're dealing with a type constructor. So let's start with this. And let's church encode this. Now, church encoding means we need to add a universal quantifier, but since our result is a type constructor, the universal quantifier must be for a type constructor. So the church encoding that I have shown before was for a ordinary type or a free semigroup or something like that. For a free semigroup, the type is not a type constructor. For a free functor, it is a type constructor. So therefore, the church encoding must have a universally quantified type constructor in it. And things are just going to be more complicated because here's the structure of the type expression in the church encoding of a type constructor. You have a universally quantified different type constructor. Then you have a function from your type to that type constructor, and again from that to your type constructor. So that's the general structure of the church encoding. But because the insides are type constructors, then this must be a natural transformation. So this must have another universal quantified type inside. So I use this squiggly arrow to indicate universally quantified functions such as natural transformations. It's the same arrow, it's just suggestive so that I keep track of where I have universally quantified and where I don't. So if you follow this structure, then this is going to be the entire expression for the church encoded free functor. Now this is starting from the tree encoding. We have a choice. What do we church encode? Do we church encode this, or do we church encode this? And there are going to be two different church encodings. So starting from the tree encoding, that's what we need to do. Now, there's one interesting side of the church encoding that I'm going to explore in more detail now, which is that the recursive use of the type is not seen in the church encoding. Instead, you replace that with this universally quantified type constructor that is present, so this P. So instead of the recursive use of free functor here, I have this universally quantified P. That is a very important part of how church encoding works with recursive types. And just before we go through that, I want to remark that in this expression, the quantifiers cannot be moved. You cannot move this quantifier to the outside. It is really inside these parentheses that the C is quantified. So for all C, this function is given. So for all C, this function is given. And that function is the argument of the outside function. So this is important for the church encoding. So you have several layers where types are quantified. And this type quantifier is specific to the free functor. This wouldn't appear if we had no type quantifier here. So this is specific, but this would be always true for any church encoding of a type constructor. You have a type quantifier inside that cannot be moved to the outside. And of course also you cannot move this existential quantifier to the outside. So for this reason, when we write code, we have to take care to hide these quantified types at the right place inside the data structure. So let's look at in more detail at how church encoding deals with recursive types and with type constructors. So let's consider an example. Here's a recursive type, not a type constructor. It's just a type with fixed type Z. It's a tree with leaves carrying values of type Z. The church encoding of this type looks like this. So I'm looking directly at our encoding of the free monoid, which was very similar. And this was the encoding, the church encoding of the free monoid. So we know this is correct. Now let's look at how it works. We take this expression, which uses the type P recursively twice, and we write it here, but instead of the recursive type P, we replace that with X, where X is the universally quantified type given outside. So in this way, the church encoding replaces the inductive use or recursive use of P by using this parameter X. So the result is a non-recursive type expression, or at least it doesn't look recursive. It does not use itself somehow to define its type. But it is equivalent to this recursive type. So it's very interesting that just by using a type quantifier, you can remove type recursion. Well, at least on the surface. You don't, of course, actually remove it, because the type is equivalent. It still encodes a tree with z-valued leaves, so it's still a recursive type or a recursive data structure. But its encoding does not show recursion. So that's interesting. So how shall we understand the way it works? This is a run method of a declaratively encoded DSL. And so this method tells us that in order to extract a value, what you need is to be able to extract a value from this. And here you have again these values. How would you ever get the value x in practice? In practice, you would have to call this function on a z several times to get some x's. And then you would put these x's in here, call this function again to get some more x's, and so on. So in practice, it is a recursive process. It can encode recursion. But all of this is already encoded in this function. So the type does not show recursion. So in other words, how can we produce a value of type x? And we don't know what that type is. We're required to write code that produces a value of type x, whatever the type might be. Well, the only way is to use this function somehow. And this function requires us to give this as an argument. So how can we give this as an argument? Either we give a value of z as an argument, and then we have our x, we can return it. Or we give two x's as arguments, and then we have a new value of x, and we can return it. But where do we get the two x's? Well, we still have this function. So again, either we give some z to this function, or we give two x's to this function. So this is where the recursion comes in. In order to produce a value of this type, we need to have a tree with z-valued leaves. And once we have that tree, we can write this function. So these functions are equivalent to trees with z-valued leaves in this way. Now, we can generalize this construction to a recursive type defined arbitrarily like this. Now here S is an arbitrary functor that is fixed, and this functor determines the structure of the step of recursion. So for example, in here, this functor would be SP equals Z plus P times P. So this functor, I call this induction functor because it describes one step of the induction when we derive values of the type. So what we have seen right now suggests that the church encoding of this recursive type looks like this. So this is a general way of encoding recursive types by church encoding, and it's not recursive, at least on the surface. And I will show an example of church encoding of list of integers. Let's see. So here's an example of church encoding of list of integers. First, let's do the recursive encoding, just for reference. It would have a sealed trait with two case classes, one representing the end of the list, or the empty list, and another representing non-empty link, in other words, a value of integer type and a next value. Now, Scala does not allow us to do this. This would be the short type notation, but this cannot be done in Scala because Scala does not allow you to do universal quantifiers like this explicitly. So instead, we denote first this as some helper case class, CP, just to make it easier for us. And well, we could actually probably define this as a type rather than as a case class, but let's keep it like this for clarity. So this CP of A is just a helper case class that represents this type. It represents a product because we can simplify this function as a product of two functions, 1 to a and this to a. And then we can simplify further. 1 to a is just a, and this is like that, just for convenience later. Now it's very easy to encode the church encoding of the list of int. It's just a function from CP of a to a. Now, if you look at what that type signature is, it's very similar to the type signature of a fold. It's a function from a and this function, which looks like an updater function for fold, and it gives you an a. And a is arbitrary, so here a needs to be hidden inside the trait as a universal quantifier. So as I said before, that's how we need to keep in mind that this is universal quantifier, and therefore we do a method in a trait. So we don't do a case class parameterized by a hidden parameter. That would be an existential quantifier. We do a method in a trait because it means that this method can be called with any parameter unknown at the time of defining this method, and that's what the universal quantifier does. So, okay, we're done. We defined this type. Let's define values of this type. So, to create an empty list, we need to write this boilerplate. Now, how do we implement an empty list? Well, we need to implement a function that takes this and returns that. Now, this has two functions inside, and we need to think about what these functions mean in order to be able to implement anything here. So what do they mean? Well, these functions mean what to do. Well, look at this, for example. What to do when the list is empty, how to run the list or how to fold the list, what is the result value when the list is empty. And this function tells you what is the result value when the list is not empty. It has a head value x, some type integer, and it has some additional rest values which have been already evaluated or folded, that your value a is given. So what do you do then? How do you update your fold value? Now, an empty list would never get into this case. It will always just give you the a. So therefore, this function for an empty list ignores the link function and just returns whatever the end is. The empty list, when folded, always gives you just this value, which is denoted by end. In the fold signature, this is denoted by init, but we're trying to imagine the list being created, so there's an empty list or end of the list. But that's just the name of the variable. So for this reason, that's the implementation of an empty list in the church encoding. Now let's do the list with one element. How do we do that? So we need to fold, and in order to fold with a list with one element, we need to use this updater function on this element and on the rest of the list, which is empty, which is going to always evaluate to the end value. So that's therefore the implementation of a one element list. So this is now more suggestive that we are having a one element list linking x to end. So this could be a case class like this in the case class encoding. But notice we don't have any case classes here representing lists. All the lists are functions. The CP is just a convenience type. We're pattern matching here just for convenience. We don't need to do that. If we, for example, encoded this just as a tuple of two values, then we would not need the case expression. We would just take this _1, _2, and so on. But it will be less readable, so that's why I write it like this. Let's implement appending. So we have an element X and a previous list. We want to add this to the list. What we need to implement is how to run the resulting list, or running a list means folding it. We are given the initial value, well, the link function. Now we need to use the link function on the X and on the rest of the list. But the rest of the list is this. So we need to run this using the same fold information. So the CP case class encapsulates all the fold information we need in order to run the list. So we run it with the same fold information, we get the value, and then we update with the X. So this is how we append. Now folding is just the same as run. So we can implement a fold function with this type signature, and it's just calling run with these arguments. Notice that fold is non-recursive. The fold function is non-recursive. Actually, none of these functions are recursive. We can implement converting to ordinary list just as a fold with a list constructor. We can implement map. Again, this is going to be non-recursive because we're just going to pass some modified folding to the list. So how do we fold a list after mapping? We just fold it with a modified function. So instead of x's, we substitute f of x. That's all. This is not recursive. So the map is non-recursive on these lists. The fold is non-recursive on these lists. All the recursion is hidden inside these functions, the run functions. Those run functions will call other run functions recursively, but we don't see that. Our code here is not recursive. Here's how we implement head option. We run it on a specially crafted folding information, and that actually is an interesting observation that I would like to make, is that pattern matching, such as head and tail, is not directly available on this data structure. This is a function now, it is not a bunch of case classes. We cannot directly pattern match on it and determine if it's empty or not, for example. We have to run this function on some arguments, and this run could take a while. So, for example, tail cannot be implemented efficiently as a big O of 1 operation. It has to run the list to the end and build the tail as a second list. So that's a deficiency of the church encoding. But if you need pattern matching operations, you need to run the structure or the entire function, which might take a while. So let's run some tests here. We implement just some function. So here's how we create. This is just a folding with a sum. Here's how we create some lists in the church encoding. So it's a pure of 10, which is a 1-element list. We append 5 to this. We get a 2-element list with 5 and 10 in it. So then we check that the sum of these elements is correct, and converting it to list gives you what you expect, and the map gives you what you expect. Now, the map operation here is perhaps stack safe. We can check that. The sum is stack safe. So our fold implementation is stack safe. Creating a list of many elements is stack safe when implemented in this way. So what we need to do is we need to compose many links together. But this needs to be done in a stack safe way, which is why we do it by hand here. We don't just do link, compose, link, compose, link. Writing this would actually not be stack safe. We'll see that later in more detail. Also, appending many elements is not stack safe. If we append a large number of elements, then trying to run that list or do anything with it would be a stack overflow. So you see the sum function itself is stack safe as long as you can run the list inside it, but it's the list itself that needs to be stack safe now. The function that constructs the list is a function that builds other functions, and that function needs to be stack safe. It should, for example, avoid composing many functions, but you can't avoid that if you do appending one by one. So you need some more clever implementation, which is possible, but I will not discuss it right here. Let us see that the church encoding of a type constructor. So I'm using this notation with a bullet to denote type functions. So the Scala syntax for that would be this. So the church encoding, let's begin with the church encoding of a type function P. Just a type constructor P. So what is the church encoding of that? This is the church encoding of the type constructor P. You have to have two quantified types, and one of them is a new type constructor, which is quantified. In other words, this is a function that is parameterized by an arbitrary type constructor f, and its argument is a function that's parameterized by an arbitrary x, which has this type signature. So this function, or alternatively you can denote it like that, with this squiggly arrow that I'm using. It's the same, I just want to have a different notation for this. It resembles a natural transformation. However, these P and F are not necessarily functors, so we don't necessarily have a naturality law. It's just a generic function parameterized by parameter x with fully generic code, but if these are not functors, then there are no naturality laws imposed in this. So this is not a natural transformation, but the type signature is exactly the same. So this is somewhat complicated, and for this reason I'm going to show you an example of how to encode the option type, the option type constructor in the church encoding, so that you see how all this is translated into code. So the direct encoding of option would be a polynomial data type like this, and with case classes that you could call like this. So we're going to implement this type expression now, where this is going to be the first type parameter, and this is going to be a second type parameter, which is inside this argument. So let's first encode this argument as a separate type for convenience. So this argument is a function that extracts a p from an option. So it looks like a natural transformation from option to p, except p is not necessarily a functor here. So let's denote this x option, which is this extractor from option. Now this x option, just for convenience, we define this type separately, parameterized by p, but it is not parameterized by x, because x is the universally quantified type, which needs to be hidden inside this x option. So therefore, we have methods in the x option that are parameterized by x. Now, I could have just had one method here, such as apply, with parameter x, and then I would have this function as the type of that method. But it is actually more convenient, especially in Scala, to have separated methods. So if this is a typical pattern, you have a function from a disjunction to something is equivalent to product of functions from each part of the disjunction to that something. So then the equivalent type is this, and we can just denote each of these as a separate method in the trait. So that's just convenience. We haven't done anything really, we just equivalently transformed this type for convenience. It's a little easier to read, and we can give these trait methods suggestive names. So having defined this type, it's now easy to define the church encoding of the option, which is parameterized by a. Notice this entire thing has only one type parameter, which is a, that is visible outside. The type parameters p and x should not be visible outside. They are hidden inside this type expression. So therefore, we put the type parameter a outside, and the run method, I just call this run for convenience to suggest what the church encoding does, is that it runs a DSL program with an interpreter. So this is an interpreter for the operations of the DSL, and this entire thing is the runner of the DSL program into an arbitrary target type. So that's why I always call these methods run. But this is just the name, doesn't do anything by itself. It is the type that do all the work, the types. So the run method needs to be parameterized by the parameter p, which is itself a type constructor. And this is the type of the run method. So that's it. We have finished implementing the church encoding as a type. Now we need some helper functions so that we can easily create values of the church encoded option. So how do we implement, for instance, constructors, sum and none? Now these are not these trait methods. These are our methods. I mean, we could make these methods private if we wanted to. This entire type could be made private. The user should not have access to it. So to define sum, we need to put an x of type A into the option. So how do we do that? We define this church encoded option with the run method, and we need to implement this. So how do we run a non-empty option? Well, clearly we use the sum method on the x value that we have to get a p of x. So that's what we do here. How do we run an empty option? We use the none method, which has no arguments and gives us a p of x. That's it. A lot of boilerplate, as you can notice. All of this is boilerplate. All of this is boilerplate. This is the actual code implementing the constructors for the option. There are some libraries that make it easier to use, but it doesn't matter for now. So we can also show that option, the ordinary option, is equivalent to the church-encoded option. To do that, we do a wrap and unwrap methods, let's say. So first we take an ordinary option and we implement the church-encoded option. And that's very easy. We just do one of these two constructors. Unwrapping from a C option into an ordinary option requires running the C option. Again, we have the same phenomenon that if you want to pattern match, for instance, you want to detect whether this option is empty or not, you have to run it. There's nothing you can pattern match directly on this value because this value is a function and you cannot pattern match on code of functions. So how do we do that? So we need to run it, but to run it on what? We need to provide an interpreter. So the interpreter will take our church-encoded option and produce an ordinary option. So that's what we need to produce. And these are just the standard methods of the standard Scala option. And that's it. So here's how we can use it. So we can create some values of option type. Now, pattern matching does not work. We cannot directly implement pattern matching. So if we tried, there's a type problem. So for example, we wanted to pattern match directly, like this, by running the option on something, but we can't really do that because we need to provide an interpreter that interprets arbitrary type X under the option, but we only have a specific types here, type A. So if we write this code, which would be kind of what we want, we get a type error. So the only way of doing a case expression would be first to run this like this, to unwrap it, convert it to an actual option with case classes, and then you can pattern match on those. On the other hand, natural transformations work fine. They don't require running on first on a real option. You can just run on a constructed interpreter and interpret this into another functor. So that's that works fine. And here's the test code. So now, finally, let's look at how the church encoding works for a recursively defined type constructor. So this is very similar to how it works for a recursive type, in that all the recursive usages of the type constructor are replaced by this type that is universally quantified. And since now we're dealing with a type constructor, we need to adjust our notation so that we define, first of all, a recursive type constructor like this, where S is now a functor that describes the induction principle, but it's now parameterized by this type constructor. So this notation that I'm using for a higher order type function, in other words, it's a function of types that are themselves function of types, and the Scala syntax would be like this. So an example of that would be a list recursively defined like this. And if we define S like this, then you see the P parameter, P, denotes the recursive use of the type constructor in its recursive definition. So this is how we could denote this construction. And then the church encoding of this looks like that. So very similar to the church encoding for recursive types. And it's non-recursive. It's a type expression that does not require recursion. So let's see how the list constructor is defined in the church encoding. This is the type expression for the church encoding of a list, because this is the structure or induction functor for list we just saw, and I'm just adding all the type quantifiers explicitly. I have a B, which works inside these parentheses only, it's hidden, and then I have a P, which gives me this, this, and this. It's also hidden from the outside. I can equivalently transform this type signature into this, where I again replace a function from disjunction to P of B by a function from just part of the disjunction to P of B, and then from this part of the disjunction to P of B, which I simplify to just P of B. So that is how I would simplify it. Now I will deliberately write code similarly to the non-parameterized list that I did first. So the end needs to be parameterized by this B. Now I used X instead of B here. And now finally I church encode the list of A just as a function from this to P of A. Very similar code that I had before. In order to define empty list, a list of one element, and appending. There's a difference that the link and the run, I'm getting them as methods of a trait, whereas before I was getting them as parts of a case class. I could have done a trait before as well, because really it's just a convenience, but here I could not do case class because I need this type parameter. Well, I denoted it as B. Let me rename this actually, just for consistency. This type parameter B that I have here needs to be hidden inside the type CL, which is this type, which is the argument of this function. And case classes will not do this for me. So I need a trait with methods in Scala. Other than that, the code is very similar. Fold is non-recursive. In order to implement fold, I need to have a bit of a typecasting, because the only way to get anything out of the list is to run, but I need to run on an interpreter. And if I'm folding, I'm not interpreting into another type constructor. I'm interpreting into a single type. So, however, I need to pretend I'm interpreting into a type constructor because that's the type signature of the church encoding. It's a run into an arbitrary type constructor. So I can choose that type constructor to be the identity functor. And in this way, I can get ordinary types out. So I define, or constant functor would be another possibility. So I define a constant functor. And then I run into that. So I give that C as a type parameter. And then I encode the running, just like I did in the fold implementation above, in this fold implementation here, except that now I need to specify this as methods of a trait rather than as parts of the case class. Other than that, it's very similar. And here I typecast x. X has type x, but I know this will only be called on values of type A. So I know that even though I'm supposed to provide this CL of C with arbitrary x, actually this will only be called on values of type A. So I can cast this safely to satisfy the type checker. Now this is a little ugly, but that's what I found to be necessary. With the constant functor being used. So, using this, I define a sum, I define toList, and I run exactly the same tests as I ran before that work for the lists. So now I would like to generalize the constructions we have seen to arbitrary type classes. So this is something that the church encoding makes particularly easy to understand, but it does not have anything to do with the church encoding. But let's look at first at the church encoding of a free semigroup. It looked like this. Now, here x is an arbitrary type, but this is a signature of the semigroup method, which is combine. So if x were constrained to the semigroup type class, then this would be given already as an implicit argument. Let's omit that argument, and I would denote it like this. So here the type class constraint is denoted here like this. So now it is an arbitrary type x which must be of this type class, and then I have this. So it's a much simpler presentation. And notice that the induction functor for semigroup over Z is this. So basically what happens is that the church encoding of a semigroup, which is this one, which we can generally write down this semi-group functor, or induction functor, as I called it before. But actually, this is always going to be of the form z plus something when we do a free type class construction, because we have to wrap the z type, and then we have these methods. This tells us how to generalize the free construction to arbitrary type classes. So first of all, we define a functor that describes the operations of the type class. So, for example, for the semigroup, we had a single operation, and writing it in this form means that Cx is just a pair of XX. But in more general type classes, Cx would be more general. And so that would be what I call the method functor. This type is in category theory called an algebra, or a C algebra. So if C is a functor, then this type is called a C algebra, which is a type parameterized by X. But I just mentioned this because the fact that it is called C algebra in category theory doesn't really help us so much. It is suggestive. Type class has some operations. These operations maybe have some laws, some algebraic laws, and so for this reason, it is suggestive to call this an algebra, but it's perhaps more confusing than suggestive. So let's just not use that terminology. Instead, let's concentrate on what these things actually do. So this I would call the method functor of the type class C. Now, I would call the type class C inductive if such a functor exists. Why? Because it appears that we're defining values of x by induction. So if this functor is given, so this is some kind of container of some shape containing x, then we can derive new values of x using these operations. So the operation is the value of this type that tells us how we can derive new values of x given some previous values. And how we're supposed to have the previous values is described by the shape of the method functor. So for instance, this method functor could have a disjunction of several parts, and each part would have 0, 1 or more x's in it. And so that would correspond to operations with 0, 1 or more arguments in the operations of the type class. So for the semigroup, the C is just a pair. For others, it will be more complicated. But given this C, we can write down a general formula for the free type class C over a type Z. So the tree encoding would be like this. So the free C generated by Z, or free C over Z, is a recursive type defined like this. The church encoding would be like this, because we replace the recursive use of the type through the type parameter x. Now, quite equivalently, we could say the church encoding is like this. It's for every x of the type class C, in other words, for which we have this value, we have this. It is then obvious that also the laws of the type class will be automatically satisfied by the church encoding after running this value. And the reason is x must be of type class C. And so after you run this, you would have a value of type class C. So whatever operations you apply to this are actually implemented in the type class C, and they therefore already satisfy the law. The type constructors are used in the same way. Here I have shown what to do with non-type constructors, with ordinary types. It's just that there's more notation and more parameters. So for example, the Freetype class C over a type constructor F in the church encoding looks like this, where you have an arbitrary P from type class C, and then you have this generic transformation or natural transformation, it might be, mapped into PA. Now, it's very important to notice where the type parameters are here. So this A is the outside A. This is the only outside type parameter that is visible. And this type parameter is hidden. And also this is a hidden type parameter inside. So we have generalized from our examples to an arbitrary type class. Let us remind ourselves what we have done. First, we started with some arbitrary type Z, and we enriched it to a monoid, which was a free monoid. We have started with an arbitrary type constructor, and we enriched it to a monad, which is the DSL that was motivated by the interpreter pattern, but this was actually a free monad. So this enrichment was done in the tree encoding by adding case classes that simply represented the operations. But there are also other encodings that are more sophisticated. And so this works for any type Z and any type constructor. And the result is a free type construction. And this type construction performs no computations. It just accumulates all the data, and it needs to be run in order to actually perform computations. And so intuitively, the free monoid over type Z adds some wrapping to Z, just enough to make it look like a monoid, to satisfy the type signatures of a monoid. It doesn't actually perform computations inside. It just adds some stuff so that the result looks like a monoid. And similarly, the free functor, it wraps a type constructor in just enough stuff to make it look like a functor. And we can interpret these free values into non-free values, into specific concrete functors, monoids, and so on by running these values. So we have seen several encodings, and running is done differently for these encodings, but all of these encodings do the same thing. They provide you a free type construction which performs no computations. It delays all the computations. It records all the data that you need to perform these computations later. And later happens when you run. So you create a DSL program. You can combine different programs very easily, and you can then run. So what are the questions that remain to us? So what are the type classes that we can construct in this way? So can we construct, for a given type class C, can we construct a free instance of the type class over a given, say, FA? The answer turns out to be yes with some type classes, no with others. So I will show examples. I already started with functor. I will show examples of these type classes, and I will show why you cannot sometimes have a free type class. Which encodings to use? This is an important question for performance. some encodings perform better than others. These encodings are not the only ones available, but I don't want to go too far into other possible encodings. And if you're interested, look up church encoding, and you would immediately see other related encodings, such as Scott encoding, Perigo encoding, and some other encodings. And another set of questions related to each other are about the laws. So what are the properties of this free instance? Can we define the free instance by its properties formulated in some way? And it turns out there are four main properties that are important. First of all, if we have a free instance of a type class over a type constructor, f, it means that we need to be able to wrap a value of f into a value of this free type class. So this free C is this free instance of a type class. So we should have a function with this type signature. Now, for second property is that for all specific instances of this type class, we should be able to run our type free instance into that specific instance, given this function. So this function, the extractor, as I was calling it before, this extractor only shows how to map the generating element or the generating type, the f, into m. And once we know how to do that, we should be able to wrap the entire free instance into m. So in other words, this generating type, the z here and the f here, has been wrapped into some stuff to make it look like type class C. And we should be able to unwrap it into a specific m, only knowing how to transform the generating type into m. So this extra stuff should be transformable automatically into the correct type class. The laws of the type class must hold after running into that m. And the last property is interesting, is that if we transform the generating type into another type, then we should be able to automatically transform the free instance as well. So in other words, the free instance should be, so to speak, a functor in f, except of course f is a type constructor, so we need to generalize the notion of functor, but it should be covariant in the type parameter f. So we should have some kind of map function that maps it like this. Indeed, if we look at this definition we had right here, it satisfies all these properties. So for example, this is covariant in f, because f is behind two arrows. This is covariant in z, obviously. So these are the properties that we will show in that whole. We already know that some of these properties hold, but we will show that more formally. What is the recipe for encoding a free type class? The recipe is this. First, the type class needs to be understood as having methods, that is, functions with some type signatures like this. And all these Q's must be covariant in P. There are some functors or some type constructors that must be covariant in the parameter P. And that is required that all these methods should have a type signature of this form. In other words, the final return type must be the type constructor that we're given. If that is so, we can put all of these queues together in a disjunction like this, call it S, and then this generic function will be a single value that represents all the methods of the type class at once. And then we call S the methods functor. So once we do that, we define a tree encoding, which would look like this. It will be recursive because these queues will have FC inside them, perhaps. But that's fine. Now, the queues might contain existential type parameters. So if these methods contain more type parameters on the left-hand side, that's fine. They will become type parameters here. And as we have seen, type parameters in case class inside a trait that are hidden from the trait become existential type parameters. And so those are fine. Those might be present. And then finally, we can implement the run method for this very easily. So if we are in the wrap case, which is this part of the disjunction, then we just map it to M and we're done. And for all other parts, these methods are run recursively. So we run recursively all the P's that are inside the queues. And then we just use the method of the type class M, which will have the same signature, except that instead of P's, we'll have specific values already of type M. And so we can just use those methods, and that's how the run function works. So this is very easy to encode. The tree encoding is very straightforward, almost mechanical. So if you have a definition of the type class, you can mechanically generate this code and its run method. There's no problem at all to generate an instance of the type class and the run method mechanically. In order to get a reduced encoding, however, you need to perform reasoning about what are the possible values of this free type class instance, and what are the laws of the type class, and how you can simplify the possible values. You start with the tree encoding, which is going to give you some nested case classes, and then you try to simplify them. And that is non-trivial. You don't have a generic procedure for doing that. So that has to be done separately in each case, for functor, for contrafunctor, and so on. So for functor, we have done this, but we will do that for all the other type classes. Finally, the church encoding can be defined either using the tree encoding, which again is completely mechanical. So you just do this. You do the S, and then you have SP to P, all in parentheses going to P, put a type quantifier on P, and you're done. Or you can do a church encoding of the reduced encoding. So that's a choice. And there might be different performance in all these encodings. So this, in other words, well, we will show more formally that this is all true. But if you have an inductive type class, which is characterized by a methods functor C, and so its methods are this algebra, the C algebra, then you have a free instance always. It has all the properties. And you have further properties. For instance, if P and Q are instances of this class, then the product of P and Q and the function from Z to P, where Z is a fixed type, are also instances of type class C. Not necessarily these. The sum or the disjunction and the product with a constant type are not necessarily parts of the type class. But those are, and this is relatively easy to prove. For instance, if you have this and this, it means you have a P as an instance of C and you have a Q as an instance of C, then you can derive this very easily. Just project this to this, project out the Q. C is a functor, so you can do that. Project out the P to get CQ, get your P, get your Q, get their product. So that's very easy, and similarly you can do this. But you cannot implement the disjunction, for example, because you would need to decide which part of the disjunction you have, but you can't decide that because you have a C of P plus Q, and it's not necessarily that you can decide which part of the disjunction it must be. So that function cannot be implemented without losing information, and so that won't satisfy Lewis. Similarly, you cannot get ZP because you would need to create values of type Z, but you don't have them necessarily, unless Z itself is also an instance of the same type class. And indeed, we have seen, looking at all the previous type classes that we analyzed, functor, contrafunctor, applicative, monad, and so on, they all have this property. The product of two type class instances and this construction always again give a new type class instance. So that is why, because they are inductive. All inductive type classes have this property. And type constructor type classes have the same property, just that the methods functor needs to be encoded like this. What type classes cannot be tree encoded? They're not inductive. Well, one type class that's not inductive is traversable. And indeed, this is not true for traversable. This construction does not work for traversable. If P is traversable, then a function from some type Z to P is not traversable. In general, any type class that has a method that's not returning a value of that type, that's not inductive. The reason is methods must be of this sort. So if you have methods not of this sort, that do not return values of this type, then it's not an inductive type class. So here's an example. Imagine a type class for a type constructor PA, and it has two methods: point, which inserts a value of A into PA, and extract, which extracts a value of A out of PA. Now, this would be of this form, because it returns the type constructor, but this is not. It returns just a bare type A. And so this type class that has both of these methods is not inductive. It does not have a representation of methods through a methods functor, like this or like this. And therefore we cannot do a free construction of it using trees, and we don't know how to encode free instances of this class. Traversable functor is another example of non-inductive. Now, just to mention that if all methods of the type class have the opposite form, that it consumes a value of this type constructor and then gives you something like this, But if all methods are on this form, not just some, so this is still not good enough, because some methods do not consume values of this type class, of this type constructor. But if all methods are of this form, they consume PA and return something, then there's another way of doing a free instance, which is called co-free, and these type classes are called co-inductive. I'm not going to describe them in this tutorial, but perhaps in another chapter. So before going to a free contrafunctor, let me go to the code of a free functor, which I have not yet shown. But actually, here's the code of what I was just talking about. I can define a free instance of any inductive type class, and I can write code for this generically. So it's a free instance of an arbitrary inductive type class. Now this is not for type constructors for simplicity, this is just for ordinary types. So this would be for semigroup, monoid, and such type classes. And here goes the wrap and the operations. So the operations contains a C of free. So this is the definition that I just showed of the free constructor. So that is the ops, and basically that's it. We can show that it has methods of the type class, and we can write the run method. So you see the run method is fully generic. All it needs to assume is that C is a functor. C, not anything else. C is this methods functor. And I'm done. So the P method C is the evidence that the type P into which I'm running is an instance of type class C. So this is a value that encapsulates all the required methods. So that's why I call it P methods C. So P has all the methods of C. And this is a very easy code that just checks whether it's wrapping, then it runs the extractor, or if it's the operation, then it runs the methods of P on the result of running under map. So I'm required to run under map because I'm under the C. I'm in here. I need to run this first into a value of P under map of C. So then I get C of P, and then I can use methods to convert that to P. That's how it works. And as an example, I use this fully generic construction to define a free semigroup. So this is the methods functor for the semigroup. I show it as a functor. This is a free semigroup. That's it, generated by string. Now this is, just to be clear, this is my own definition here. It's not the CATS library definition or any other, or Scala Z definition. I believe in those libraries, what is called free is actually the free monad. It's a free monad and not just a free constructor of any type class. So in my definition here, it's a generic free instance of a given type class for inductive type classes. And here's code that creates some values and runs them. So I create ABC, XYZ, wrap them. Then I use operations to add them. And I run this into a string and I'm done. And I can do the same with the church encoding. It's slightly more type definitions, but it's exactly similar. The church encoding is this type. Equivalently, it is this type. And so I just define the trait for the argument, and then I have this, and then I can show that it's a type class. Now, the showing that it is a type class is actually non-trivial. This church encoding must have methods of the type class C. In other words, it must have a function of this type. C of the church encoding must be mapped into the church encoding itself. And the types here are different. There's an all X inside here and all Y inside here because they're different. So this actually is not very trivial to derive. You just need to be very careful in following the types. And here's how this works. So how can we get this value? Now, we would get this value if we had a z. Well, we don't have a z, obviously. All we have is this. We have c of something. So it looks like our only hope is to get this c of y, and then we would have a function from c of y to y that we can call on that c of y, and that gives us the result. Now, we are given this, so we are required to be able to work with an arbitrary given y. So imagine we're given some y, but then we have this function which has an arbitrary x inside that we can set. So this function accepts arbitrary x's. So let's set this x equal to y in that function. And then we would have a value of c with y in here, z plus c of y going to y. But we have a z plus c of y going to y. We're given that value. So we can substitute that value in here, mapping under c, so that we can get a c of y as a result. So then we get a c of y, we can put it in here and get a y out. So this is a little convoluted, but that's the code. We map under C, given a type parameter y in here, to run the free instance, and then we use the ops on the resulting cy. So this gives us a c of y. We run the ops on it, we get a y, and that's what we return. So if you want to understand exactly how this code works, you would have to write it yourself. It's a lot of manipulation with types. All these types are parameterized, so this is kind of technical and not so easy to see looking at the code. But this is the only way to implement the required type signature, which is this. And now we implement the wrap, which is straightforward, and the run, which is straightforward by using these methods. So this, again, we run the semigroup example, exactly the same code, up to some syntax changes, gives exactly the same results. So let us now look at the functor. So I already showed how the functor here the free functor is implemented. And I derived the tree encoding and the reduced encoding. And then I started to talk about the charge encoding, and that actually was so complicated that we had to go through much slower through all the parts that are required. So let's now look at the code for the free functor. So the free functor actually starts from a given type constructor. So it's always a free functor generated by a given type constructor, or a free functor over a type constructor. And the type constructor doesn't have to be a functor. And actually, in many applications, it is not a functor, and it cannot be possibly a functor because it has index types with specific type parameters, parameterized types with non-free specific assigned type parameters like this. So I call these things unfunctors. It's a funny term that I think is appropriate here, because it is like a functor because it's parameterized by a type, but it couldn't possibly be a functor because of the way it's defined. So this unfunctor could be seen as describing two operations in some business logic, where you add the name to some database, say, and you get an ID back, and then you get name by ID, and this name may or may not exist in a database, and so the result is an option of string. Now we would like to transform this unfunctor into a functor, run some program with it, and then transform that into an ordinary option of some result. So you see, sometimes you would have an option of string, sometimes not. So let's be safe and run this into an option. So in order to do this, we need to define an extractor or interpreter for this type constructor into option. So this is this type, which is natural transformation, but actually it doesn't have to be natural transformation. It's just a generic transformation from one type constructor to another. And I'm using the cats library type. That's defined there. So how do I transform? Well, there are two cases. If it's a long, then I just transform it into a 1. And if it's an option string, then I transform it into none. So it doesn't matter. It's just an interpreter of some kind. It doesn't. All it does is gives me an empty option or a non-empty option. It doesn't really do a lot of good. So that's what I'm going to be using. So I'm going to write now a free functor based on this free functor over this unfunctor. I'm going to write some maps on it, add some transformations, and then run into an option. So that's going to be the example. So here's where the code starts. This is the tree encoding of the free functor. I have the wrap case class, I have the map case class. Map case class has an existential type B. I define the functor instance for the type class functor. And the map method does nothing, it just creates a new wrapping with the map type class, case class, sorry. Then I have my function here, which creates a free program, free functor program. All it does, it applies map to some given value, many times. So this number of iterations is given, so that many times I apply map with the same function to that value. So this is just a test. I'm going to start with some value, wrap it, and then map many times. The runner, I'm trying to make it stack safe, and that's a little bit of a problem actually, and here's why. I will have a lot of nested case classes. I'll have to go through all of them. So the unfold function that I'm defining here is going to call itself, and so one thing I could have done is just apply the map. You see the f of z is a free functor value. I could just have run it through the same function and then apply the map with f to it. But that would have been not stack safe. So I did another thing. So I did a tail recursive unfold where I first accumulate. So what I did here actually is I did and then. First, that was my first implementation. Every time I have a map, I have a new function. So the result is this accumulator that I have in the unfold. And so I just accumulate all the functions inside the maps, and I run them only at the end. So I run this only at the end. So that's the idea. So that is tail recursive, and then I hope to be stack safe, but I'm not stack safe. This will actually give me a stack overflow. And the reason is the and then is problematic in Scala. And that was quite surprising to me because it's not so in Haskell, and I didn't expect it, but and then is actually not stack safe in Scala. Here's why. Here's my sample test code that shows why this is so. Let's compose a large number of functions and call the resulting function. So here's a code that does this. Let's just compose a lot of functions. All these functions are just adding one to their argument, and so that's very simple. But if we do this with a large number of functions, we'll have a stack overflow. So whatever we do, we'll have a stack overflow. We can compose these functions, or we can directly compute. Still we have a stack overflow. So the reason is that composition of functions introduces another stack frame, and that's unfortunate, and it cannot be removed apparently in Java, in JVM, for technical reasons. So you could not have a compiler that automatically removes this extra stack frame. So what do we do? Well, Cat's library includes this and then structure, which you can use. And if you use that, so if you start with this and then you compose with more functions, then this is stack safe. How does it work? It doesn't actually compose these functions until much later, until you need to run this function, and then it actually accumulates all the functions you give it in a list, and then it runs that. So I implemented the same kind of thing, which I call safe compose, using the data structure called chain, which is from the Cats library, which is a very high performance list. And so here's what I implemented based on somebody's suggestions. Michael Pilquist suggested this. So I just did a bit of code massaging. So now the idea is that instead of composing, you wrap the function into this chain F data structure. And then composing this with other things doesn't actually compose functions. It adds to the chain of functions. So these functions are all stored in a list. And only after you run them, so the apply function is called, then you fold over the chain and apply these functions. So that's how it works. And I made it so that you can compose on the left or on the right with the chain, and you get a chain again. So that's what I did, and the result is good. So it's actually faster than using cat's library and then. So that's what I had to do. I had to use here, I had to use before. So before is my replacement of and then, which is easier to use than cat's library, and it is faster. So this is what I would do if I didn't have this. I would accumulate results functions in a list, and then at the end I would fold over that list. So this is kind of uglier, and it's better to put this code into a library. And here's a benchmark. The free functor in the reduced encoding, it has fewer case classes, but it has a more complicated map, because now it needs to do this in the map. Notice that in the tree encoding, the map didn't do anything. It just wrapped the data into a new case class. But in the reduced encoding, the map method of the functor actually performs a computation. It already composes the functions, although we're using this smart composition, but that's what you need to do. Before and after are the smart methods that I implemented to replace and then and compose in the Scala. And then I do the same testing, and it's slightly slower than the tree encoding,